for this approximate problem, you can say that you have a unique solution UN, which is C1 in time, global in time, with value in chi n of d of L2 sigma. Okay, L2 sigma, that's solenoidal divergence-free L2 field. Okay, L2 sigma, that's divergence-free L2 field. And this, as I said, is a set of very regular functions in any HS. Okay? But here, okay, to say that it's C1, I have to fix the topology of this, and I would say it's a subspace of L2 sigma. So you can see this as a closed subspace of L2 sigma. Right? So for this approximate problem, you have a global in time, smooth and even very smooth solution. So why? Why is this much easier than the original Euler? Because we will start from a field that has frequencies less than n. And we will preserve this through time. But for functions that have frequencies with compact support, the gradient is the continuous operator. Right? So you don't have a PDE here. You have an ODE because the gradient acts continuously over functions that have frequencies less than capital N. Okay, so first thing to notice is that the equation in this approximated Euler problem can be seen as an ODE with phase space this chi n of d L2 sigma. Okay? Because I start from an initial data which is in this, it will be preserved by the evolution. The gradient acts continuously, just like a function acting over this space. Alright? So that's an ODE. That's an ODE. That's my nonlinear function. And this is smooth. Here. It's bilinear.
So here you have said it's all cap.
Okay, no, so at this stage, I just have local in time solution with Cauchy-Lipschitz. Okay, so that's the first thing. I have a local in time solution, UN, which is C1 of 0Tn with values in chi n of d L2 sigma. Okay? By Cauchy-Lipschitz theorem for ODEs. But as Frank said, I claim that the solution was global. Okay? So prove this. It's enough to prove that the L2 norm of UN does not go up. And why is that? It's because on this equation, okay, and the divergence of u should be 0 here. So, divergence of u should be 0. On this equation, I can perform again an energy estimate. Okay, so I have dt un plus p of un dot grad un equals 0. The divergence-free condition gives me this. I multiply by un, integrate again. And then I get that the 1/2 of d over dt of un n2 squared is 0. So I get that 1/2 of un n2 at time t squared is less than 1/2 of un of 0, which will be less than the original L2 norm of u0. So it tells me that this norm does not blow up. Okay, and for ODEs it will be enough to say that the solution is global.
So here the first inequality should be equality.
Sorry?
So here you should have an equality.
Yes, sorry, I have an equality here. Thank you. So there is no blow up for this L2 norm. So by standard results for ODE, UN is global in time. So I have local in time by Cauchy-Lipschitz, but with this additional information, I have global in time. Okay. Okay. So this concludes my first step, my regularization. I have this approximate problem. I have a nice solution, U capital N. But of course, what I want in the end is to solve Euler. Okay, so I want to get rid of this truncation. So I will take higher and higher frequencies. I will let n go to infinity, and I will see what happens. And so the key step will be to get uniform bounds on my sequence of approximations to n. So, yes?
What is L2 sigma?
What is L2 sigma? So L2 sigma is, sorry, that's said that more clearly. It's divergence-free L2 field. So that's so L2 sigma. That's H0 sigma. So that's the fields in L2 which are divergence-free, right? This is U in L2 of RDD. Is that okay?
Okay, maybe
Oh, and divergence U is in the distribution sphere. Yes. So that's what I called it H next time, last time. That was the space on which the Lorry projector was projecting. Yes.
How did we get EN from E?
Oh, how did we get EN from E? Oh, you have to think of it, I mean, we did not deduce it from E. It's an approximation of E. So I just added this. And I just added this on the initial condition. So it's kind of a different system, which looks close. And the point is that at each step, I look at frequencies that are less than n. I cut any frequency which is higher. So it means that derivatives will be nice on this kind of functions. Okay. So that's why it's easier. But it's not deduced from E, it's an approximation that I take as a new system. Any other question? So now that I have these nice solutions, I want to get uniform bounds, right? I want to get uniform bounds. And okay, the main proposition actually is the following. You can show that so S is again needed. So for any S in N, there exists some constant Cs which is independent of